to discuss a very important topic related to the unit of water, that is the determination of the hardness of the water sample using the EDTA method. To solve the numericals based on this particular topic, you need to know the basic principle and the concept of the practical related to the determination of the hardness of water sample using EDTA method. So let's first have a quick recap of that practical part. It carries actually two parts, if you remember. So in the first part, what do? We take the sample solution. If you remember, you pipette out 25 or 20 ml of the sample solution in the conical flask, and then we add 2 to 3 ml, basically 3 ml of the buffer solution, which is the ammoniacal buffer falling in the pH range of 8 to 10 to this sample solution. And then we add EBT indicator, which is actually originally blue in color. Now remember, you are going to determine the hardness of the sample solution. So definitely the calcium and magnesium ions are present in my sample solution. So in the conical flask, when I add buffer solution to this particular sample of water, actually it originally contains calcium or magnesium ions. I have added buffer to this solution because I want to maintain the pH of this particular solution in the pH range of 8 to 10. Why? Because my indicator which I am going to use next is actually pH sensitive. So then I add indicator, that is EBT, Erythrome black tea, which is originally blue in color. The moment I add EBT to this particular solution after adding the buffer, what happens? All the metal ions, they come and get attracted towards EBT, forming a complex with EBT, which is actually metal EBT complex. This complex is unstable in nature. Why? We'll come to know in the second phase, in the second step of this particular experiment. And the color of the solution, which was actually colorless initially, okay, has now changed to wine red. Okay. So my sample solution was colorless. I added EBT. The moment I add EBT to this particular solution, it becomes wine red in color. Why does the color of the solution changes? Because EBT is no more in the EBT state. It is now in the state of a complex, which is metal EBT complex, which is actually unstable in nature. So this is the wine red color that we get. Now what do I do? If you remember, while performing the experiment, after adding the indicator, you then turn the knob of the burette to add the standard solution. What is the standard solution which is taken in this particular experiment? It is disodium salt of EDTA. So this is the standard solution. Remember, why do we take disodium salt of EDTA? Because EDTA itself is sparingly soluble in water. It is not soluble in water completely. So we take the disodium salt of EDTA, which actually is completely soluble in water. Okay, so we get the solution, standard solution in the burette, and then I add that standard solution to my conical flask component. What was my component of the conical flask? Now my conical flask actually from the first phase or the first step contains a wine red solution, which is actually due to metal EBT complex present in my solution. Now to this wine red solution, which is actually due to metal EBT complex, I start adding drop wise the standard solution from the burette. Now the moment EDTA molecule comes into contact with these kind of molecules, the metal ions, they ditch the EBT and they go and join to the EDTA. So now what do I get? I get metal EDTA complex. Okay, very unfair on the part of the metal ions, but still we have to bear with it, and the EBT is left behind alone. But the color of the solution finally that we get actually is blue in color. So the end point of this experiment is wine red to blue. Why blue in color? However, the complex which is formed by the metal EDTA, that is metal EDTA complex, is colorless in nature. This is very important on the from the aspect of the experiment viva also and the theory part also, because usually students feel and they assume that the blue color in the end that we get is because of this complex. No. In the first phase, the color that we get is because of the complex, but in the second phase, the color that we get, the second part of the experiment, the color that we get is not because of the complex, because the complex is colorless here. Metal EDTA complex is colorless. It is due to the EBT which is now free from the complex part, which is alone here over here without any metal being bonded to it. Now, since the metal ion have broken their bond with EBT or from EBT, and so this complex, the wine red complex, is unstable in nature, whereas the final complex that is formed between metal EDTA is stable in nature, because the metals, they don't come out of this complex, they don't break the bond or with EDTA. So the final color, the end point, is wine red to blue numerical part. It consists of 3 steps. Just try to concentrate over here. Why? Because this will give you a small trick. We'll straight away come to specific formulas and then do the numericals. We will not go into the deep details and derivation how those formulae come. Okay, so step 1, step 2 and step 3. The first step actually involves standard hard water. So I have taken standard hard water over here. I have represented with HHW. How do I prepare the standard hard water? Actually, this standard hard water contains 1 milligram of calcium carbonate in 1 ml of distilled water. Remember, the word standard means the concentration. So what is the concentration of this standard hard water? 1 milligram calcium carbonate in 1 ml distilled water. The second step consists of the unknown hard water. There is a hard water sample. I do not know the concentration. Definitely it contains calcium and magnesium ions. So whenever I use this unknown hard water, I am going to get the total hardness value from it. The third involves boiled hard water. I have taken the unknown hard water, and then what I do is I just boil the water. You know it very well. After boiling the hard water, the temporary hardness get removed and it is only the permanent hardness which is left behind. So the data that I'm going to get over here from this boiled hard water is the permanent hardness of that particular sample. Now if I subtract permanent hardness from the total hardness, definitely I can get the temporary hardness of that particular water sample. So there are 3 phases or 3 steps related to the numericals. Now let us say that the volume of standard hard water that I have taken is X ml. Now since from this particular data which says 1 ml distilled water containing 1 milligram calcium carbonate, so definitely since 1 ml of standard hard water, because it is in 1 ml distilled water, so the total volume will be 1 ml definitely. So since 1 ml of standard hard water contains 1 milligram calcium carbonate, so definitely X ml of standard hard water will contain X milligrams of calcium carbonate. Now let's say the volume of EDTA, which is the standard solution, if you remember, used in a particular experiment when I am going to determine the hardness of the sample solution, is V1 ml. Okay, so V1 ml of EDTA is capable of neutralizing, okay, X milligram of calcium carbonate. So for this particular value of the solution, for this particular concentration of the solution, I am using EDTA, and for that titration I am able to use V1 ml. So definitely I can say that V1 ml of EDTA is capable of neutralizing X milligrams of calcium carbonate. This is one part of the data. Now let's say your numerical gives you the volume of unknown sample, okay, of water, which is definitely hard water. So how much hard water do you pipette out? It is Y ml. Okay, for this Y ml of hard water, let's say you use the volume of EDTA from the burette. Okay, volume of EDTA taken or used, I should say over here, is V2 ml. Okay, so what will be there? Let's see. So total hardness of this sample will be equal to X over V1, which is the data which I am getting from this part, into V2 over Y into 1000. Straight away this formula will give you the value of total hardness of your sample solution. How do we come to this particular expression? I can explain that part also, because V2 ml of EDTA is equivalent to Y ml of unknown sample. But if it is 1 ml of EDTA, then how much unknown sample? it will be x upon V1 into V2. Okay, milligrams of calcium carbonate in terms of milligrams of calcium carbonate. Okay, so finally we get the total hardness as x over V1 into V2 over y into 1000. So I take here boiled water according to my step 3. Okay, so let us say that the volume of boiled water taken, that is the sample taken, is ZmL in the conical flask after the water has been boiled. So, and for neutralizing this boiled water ZmL, the volume of EDTA which is required, okay, or which is used to neutralize this ZmL is V3 ml. Okay, so definitely we can say that V3 ml of EDTA is actually equivalent to ZmL of boiled water. But from the first part, from the initial part that we just discussed, you also know one thing, that 1 ml EDTA actually is equal to x over V1 milligrams of calcium carbonate. And if you remember what is x, x was the volume of standard hard water taken, and V1 was the volume of EDTA which was required to neutralize this standard hard water sample. Okay, so if it is in terms of standard hot water, let's see what we get in terms of this boiled water sample. So definitely in that case, V3 ml of EDTA, if 1 ml of EDTA is equivalent to x over V1, so V3 ml of EDTA will be equivalent to x over V1 into V3 milligrams calcium carbonate. Okay, but here ZmL of boiled water is there, so let's see what we get in terms of ZmL. So therefore ZmL of boiled water sample is equal to x over V1 into V3 over Z. Why? Because V3 ml of EDTA is equivalent to ZmL of boiled water. So we just use this information over here, and this much milligrams of calcium carbonate is there. So this is for 1 ml or ZmL only. So that implies if we want to calculate for 1000 ml of boiled water, what will be the expression? X over V1 into V3 over Z into 1000, this much milligrams of calcium carbonate. So I can say one thing over here, that for permanent hardness, the expression will be, for permanent hardness, my expression will be now x over V1 times V3 over Z into 1000 milligrams of calcium carbonate. Since we are writing hardness over here, so I don't need to write milligrams of calcium carbonate in this case. So this is actually my final expression. Okay, now we'll try to use these formulae into some numericals based on these particular formulae and the topic. Question number 1 says 50 ml of standard hard water, that is SHW, containing 1 milligram of pure calcium carbonate per ml, that is the concentration of standard hard water. When this standard hard water is used, it consumes 20 ml of EDTA. Okay. 50 ml of water sample consume 25 ml of same EDTA solution using EBT as indicated. Calculate the total hardness in ppm and degree French. Now first of all, let's see what is given from this particular problem. Okay. Now 50 ml of the standard hard water sample. If you remember, in the previous discussion, we said X is the volume of standard hard water taken. So that means the value of X from this particular problem is 50 ml, which is the volume of standard hard water taken. And then V1, what was V1? V1 was the amount or the volume of EDTA which is used to neutralize this 50 ml of the standard hard water sample. So V1 from this particular problem, how much EDTA is being used over here? I think according to this 20 ml of EDTA is used. So 20 ml of EDTA is used to neutralize this standard hard water. So this will give me V1 and this will give me X. Okay, now in the second part it says 50 ml of water sample consume 25 ml of the same EDTA. So EDTA is same but the sample has changed now. So that means Y will be now 50 ml and EDTA volume, that means V2 will be now 25 ml. Now I have got these values of X, Y, V1 and V2 from the problem. Now let's see what is the formula for total hardness. Now the total hardness formula actually is what? It was X over V1 times V2 over Y into 1000. Okay, I have got X from the problem which is 50. Okay, V1 was 20, V2 is my 25, Y is 50 into 1000. So what do I get? I simply get 1250 milligrams calcium carbonate. Okay, so that means 1250 milligrams calcium carbonate is present in 1 liter of water sample. That means the answer is 1250 milligrams per liter. But you have to tell the answer in ppm as well as in degree French. Remember, 1 ppm is equal to 1 milligrams per liter. So that means this is equal to 1250 ppm. What about degree French? You know the data, if you get a recap, 1 milligrams per liter is equal to 0.1 degree French. So that means 1250 milligrams per liter will be equal to 1250 times 0.1, that makes it 125 degree French. So my answer in degree French will be 125 degree French. This is the final answer. So by using the formula you can directly do the numericals. Number 2. It says 0.5 gram of calcium carbonate was dissolved in HCl and the solution was made up to 500 ml of distilled water. Okay, this is a stock solution of calcium carbonate that I have prepared. Okay, now 50 ml of this solution required 48 ml of EDTA solution for titration. 50 ml of hot water sample required 15 ml of EDTA, and after boiling and titrating it required 10 ml of EDTA solution. Calculate the hardness of the sample. Fine. So let's come back to the standard solution that we had prepared. Okay. Now my standard hard water, actually, which is this one I had prepared, I took 50 ml of this standard hard water, and when I took 50 ml of the sample of standard hard water, I required only 48 ml of EDTA. That means what is given over here? X is given as 50 ml, okay, and V1 for this particular X is given as 48 ml. Now come to the next part. 50 ml of hot water sample required 15 ml of EDTA. Okay, and after boiling the requirement changes to 10 ml. Okay, so Y which is given over here is 50 ml, and for this Y, V2 which is required is 15 ml. And finally after boiling, when I again titrated, I require only 10 ml. Okay, so here V3 is given as 10 ml, but where is the value of Z for the third part? Again go through the question. 50 ml of hot sample, water sample required 15 ml of EDTA, and after boiling and titrating required 10 ml. That means the volume is same. So Z is also 50 ml over here. So I have to determine the hardness of the sample. That means I need to determine first of all the total hardness, and then permanent hardness, and then the temporary hardness. Okay, so let's start with it. Okay, taking this particular data, first of all I just determine the total hardness. That is my first step, which actually has the formula of what? x over v1 into v2 over y into 1000. What is the value of x over here? It is 50. V1 is 48. V2 is 15. Okay, and what is y? It is 50 over here and 1000. So that comes out to be how much? 312.5 milligrams per liter of total hardness is present. Okay, now what do? Is I move forward, okay, and then I boil the solution and then again titrate it to determine the hardness. So that means after that what will I get? I will get the permanent hardness. Okay, so I'll get permanent hardness, which is actually equals to what? What was the formula for permanent hardness? I'll give you a second. Just go and have a quick recap of permanent hardness formula. Yes, it's coming. That's it. So it is equal to x over v1 times v3 over z into 1000. Okay, so x is x is what? How much is x? X is 50 over v1, which is 48, into v3, which is 10, over z, which is 50, into 1000. So that comes out to be how much? It comes out to be 208.3 milligrams per liter, or 208.3 ppm. So I've got the total hardness, I've got permanent hardness. The only thing which is left for me to calculate is actually the temporary hardness, which is equal to total hardness minus permanent hardness. So that is 312.5 minus 208.3, which is equal to 104.2 ppm or 104.2 milligrams per liter. It's one and the same thing. So I write ppm over here also and milligrams per liter over here, so that you don't get confused. This is how we solve the numerical in an easy way. Okay, so you just have to concentrate upon where is the data for standard hydrogen water given. That will give you the value of x and v1. Where is the data after boiling that you are getting? That is that will give you the value of z and v3. Remember, all the v's are for EDTA volume and all the xyz are for your sample volume, water sample volume. Number 3, take this question as your practice question. Try to solve it. See if you are able to do it, and that means definitely you are thorough with this particular topic. So the question says 1 gram of calcium carbonate was dissolved in dilute HCl and a solution diluted. This is not dilutive, it is diluted to 1 liter. 100 ml of this solution required 90 ml of EDTA solution, while 100 ml of sample water required 40 ml EDTA. On the other hand, 100 ml of boiled water sample when titrated against EDTA consume 20 ml of solution. Calculate each type of hardness, means permanent, temporary and total as well. So try to work this problem out. The answer to this problem is given in the description below, and I hope this video was helpful for you.